Okay, so the next example your book does is the example of an infinite line of charge. So imagine we've got a sort of wire or a string that's infinitesimally thin but infinitely long in the y direction. And that thing has a charge density, a charge per unit length of lambda. So lambda is the charge of this thing per unit length. So the little bits of electric charge that add up to, that contribute to the electric field, here we can write that dq is equal to lambda times dy. The way your book has got it drawn, the line extends up and down the y-axis, and we're located on the x-axis some distance x away. So we can write that the electric field due to this line is equal to the integral over all the little bits of electric field due to all the little bits of charge. But just like in the ring problem, every piece of the line down here in the negative x-axis that exerts an electric field in this direction has a corresponding piece on the positive y-axis that exerts an electric, or that creates an electric field in that direction. And the y components of the electric field cancel one another out. So just as in the last example, we can only, or we should only concern ourselves with the horizontal, the x component of the electric field. So the electric field is just going to be equal to dEx, okay, the integral of all the x components of the electric field, which you can write that's just equal to the integral of dE times cosine theta. So we can write that the electric field is equal to 1 over 4 pi epsilon naught times dq over r squared, the electric field due to every little piece of charge dq, times the cosine of theta, which gives us just the horizontal component. So our dq is equal to lambda dy. Every little bit of electric charge is equal to the charge density times a little bit of the line along the y-axis. R squared is not a constant. In the ring, we were always the same distance away from each piece dq, but here we're definitely not. In this situation, we're always a slightly different distance away from these little bits of charge as we integrate up and down the y-axis. So we can write that r squared as x squared plus y squared, just from the geometry of the situation. If this is x, this is y, r is equal to the square root of x squared plus y squared, so r squared is equal to s squared plus y squared. And we should also write this cosine theta in terms of x and y and r. So cosine of theta is going to be equal to x over r, where r is equal to the square root of x squared plus y squared. So we can write this whole thing as lambda over 4 pi epsilon naught. Lambda is a constant, it can come out of the integral. X is actually also a constant. It's just our distance from the midpoint of this, or from the origin. So that can come out of the integral as well. Times the integral of, what do we got here? We've got dy, and then we've got x squared plus y squared times x squared plus y squared square root. So that's x squared plus y squared to the 3 halves power. And what is our what are our limits of integration? Our line goes from y equals minus infinity to y equals plus infinity. So the limits of integration for integrating that whole line, getting all the contributions of the electric field, are from minus infinity to infinity. I don't know how to do this integral off the top of my head. You can probably do some kind of substitution, but I just typed this whole thing into Wolfram Alpha, and Wolfram Alpha told me that this integral, the definite integral from minus infinity to infinity of 1 over x squared plus y squared to the 3 halves is just 2 over x squared. So that makes this whole thing, what do we got left? We've got 1 over 4 pi epsilon naught times 2, well, I'll just do the whole thing, times x times 2 over x squared, which is equal to 1 over, where'd my lambda go? We should have a lambda here, which is equal to lambda over 2 pi epsilon 0, 1 over x. And that is our final answer. So the electric field is proportional to the charge density. That makes sense. And it is proportional to 1 over the distance from the line. That's actually fairly typical when you've got a situation where, remember I said last time that if you've got a point charge, the geometry of the situation, because that electric field goes out in all directions in three-dimensional space, that electric field tends to be proportional to 1 over the distance squared. If you've got an infinite line of charge, that electric field spreads out, this is hard for me to draw with this tablet pen, but I'm going to do my best, spreads out in the horizontal direction, but it doesn't spread out in the vertical direction because there's always some component contributing to it from the other side of the line. So the electric field of anything that's linear as opposed to a point, or it doesn't matter if we're talking about electric fields, magnetic fields, gravitational fields, that thing tends to be proportional to 1 over the distance instead of 1 over the distance squared, because instead of going out in 3 dimensions, it only goes out, the electric field lines only spread out in 2 dimensions. So the fact that this is proportional to 1 over x, that makes me happy. I'm happy with that answer, and that's the result that your book gets. One thing before we continue is this is actually not how your textbook does the integration. Your textbook does the integration by integrating not dy from minus infinity to infinity, but integrating over this angle d theta from the top of the line to the bottom of the line. So I'm going to do another example where I do this integral the way your book does it and show that we get the same answer, that the electric field is proportional to the charge density and inversely proportional to the distance.